For this problem, we're going to do an existence and uniqueness proof. We're going to prove a statement of the form, there exists a unique x in the set x such that p of x. And that exclamation point there stands for a unique. And to prove such a statement, we have to prove two things. First of all, existence, that there does exist some x in x such that p of x. And according to that statement, maybe there are more than one, but at least one. And then we're going to show that, no, there can't be more than one. There's, in fact, exactly one. And that's the uniqueness part. And that amounts to supposing that we have a y and a z in x, such that p of y and p of z are both true, and concluding from that that, in fact, y and z must have been equal. Okay, so it would be impossible to have two unequal elements of x such that p were true for both of them. All right. Prove that for every real number x, there is a unique real number y such that x squared y equals x minus y. If you want to, you can sketch a graph of this equation and get some visual insight into why it's true. Here is our goal. And the first thing to do is to let x be an arbitrary real number to get rid of that universal quantifier, and then x and r will become a given. And now here's our existence and uniqueness statement. And so we get two statements out of that. First, existence, and then uniqueness, which is spread over a couple lines here. For all a and b real numbers such that if the statement is true for a and the statement is true for b, then a must equal b. Okay. And you notice that the a and the b, they're the y, and so I've substituted the a and b for y here, not for x. All right, so let's take these two goals one at a time. We'll do existence first. And to prove existence, one way to do it is to just come right out and say what we think y is going to be. And so to figure that out, you'd want to solve this equation for y, right? Probably just add y to each side and then factor y out from the left side and divide by whatever other factor you get, and you have the value for y in terms of x. And when you do that, here's what you get. Y equals x over x squared plus 1. And then our goal becomes to prove that that y so defined is in fact a real number, and that it satisfies this equation, x squared y equals x minus y. So let's take those goals one at a time. First of all, to make sure y is a real number, the only thing that could go wrong here is if we end up dividing by 0. That's not going to happen because for any real number x, if you square it, you're going to get a number greater than or equal to 0, and you add 1, you're going to be greater than or equal to 1. Okay? So in particular, you're never going to be equal to 0. So putting all of that together, we see that y is in fact a real number. And then that leaves us just with this goal. And for that one, all we want to do is calculate both sides of the equation. So first of all, the left-hand side x squared y, if we replace y by x over x squared plus 1, which is what we're defining it to be, then x squared times x gives us an x cubed in the numerator. Whereas if we compute the right-hand side, x minus y, we get x minus this fraction. And when you combine the two fractions, you do get that same x cubed up on top. Okay. And good. So the fact that these two are equal shows us that we have obtained our goal. So let's pause there and write up what we have so far. We said the first thing was to let x be an arbitrary real number. And so that came over here, and then that was our goal. So let's write that down. Let x be an arbitrary real number. We're going to show that there exists a unique real number y such that x squared y is equal to x minus y. Great. And there exists a unique, by definition, becomes existence and uniqueness. Okay. So we're going to deal with the existence part first. And we're going to let y be x over x squared plus 1. And we'll have these as our goals. Okay. So let's start writing that up. We can tell our reader we're about to do existence first. First we prove existence. And we're going to let y equal x divided by x squared plus 1. Okay. And to get the first goal, that y is a real number, we just need to comment somehow that x squared plus 1 is non-zero. So the denominator is non-zero, and this makes sense. So let me just say, because x squared plus 1 is greater than or equal to 1, y is a real number. We don't have to say every single little detail there. Our reader will understand what's going on. And then for the second goal, which we brought down here, we're just going to sort of link the left side up to the right side somehow to arrive at that. So let me just say we compute, and there it is. So x squared y equals this, which equals this. I've only written it once. Which equals this, which equals that. And from beginning to end, we see we have what we wanted, namely this equation up here. Okay. So we've proven the two bits of existence. And now we can go on to uniqueness. So back over to our tables here. Here's what we got to show for uniqueness. And to deal with these quantifiers, we can let a and b be arbitrary real numbers. So I'll just add that to my list here, which had x in it already. And then that leaves us with this conditional statement to prove. And we can do direct proof, so move the antecedent over as another given. And we just have to prove that a equals b. And we have a conjunction here, so we can write that down as two separate givens. And then remember, I'm trying to get that a equals b, and so I need to somehow combine these equations to, I guess, eliminate the x, right? And well, one idea would be to subtract the two equations. I can get rid of this x over here by doing that, and I'll have an x squared in both terms on the left, which I can factor out. Okay. And then from there, well, we could move this over to the left side as another copy of a minus b, and then factor out that a minus b, and what's left is x squared plus 1. So we get the product of these two factors equals 0. And, well, we know from the properties of real numbers that if two of them multiply to 0, then at least one of those has to equal 0 itself. Okay, so we get a disjunction there. And the thing is, x squared plus 1 is never going to be 0, right? We discussed that earlier. Because x is a real number, x squared plus 1 is not equal to 0. And therefore, bring down our goal again, by, what was this called? Disjunctive syllogism, I believe, one version of it. We have the negation of one of our sort of options here. It rules that one out, and it means that the other one must be the case, that a minus b must equal 0. And that's precisely what we need to get that a equals b. So let's write that one down. We let a and b be arbitrary integers. And we're going to be proving that. And then to prove that, we got to bring the antecedent over as a given and prove that A equals B. So, okay, we better say that next we prove uniqueness, and we're going to let A and B be real numbers. I left out the word arbitrary, but that's okay. Satisfying these two equations, right? X squared A is equal to x minus A, and x squared B is equal to x minus B. And we're going to show that A is equal to B. And to get there, we did some algebra, right? Well, these brought us down to these two equations here, and then we subtracted them to get this one, and brought everything to the left side, and then got a disjunction out of that, and brought that disjunction together with this fact using disjunctive syllogism to arrive here, which got us our goal. So how are we going to describe that? Well, the big thing we did first was to subtract the two equations, right? So is that going to make sense? Let these be real numbers satisfying that and that. Subtracting equations, yeah, okay. So a little bit ambiguous because this equation was here, but I think it will be understood. Subtracting equations, we get that x squared times A minus B. Oops, get that out of the exponent there. X squared times A minus B equals B minus A. Or another way we wrote it was x squared plus 1 times A minus B is equal to 0. And we'll say that because x is a real number, this term is non-zero, so A minus B has to be 0. Okay, so I'll just say this implies that A minus B is equal to 0, or A equals B, which is what we said we were going to prove. So we're finished.